Hello everyone, I'm Chintan Patel from TIFR Mumbai. And this is a short description of the poster that I'll be presenting at Spring 2025. So it's on this upcoming work which we hope to put out soon. It's with these set of authors. So let me first tell you about the question that we are addressing. So suppose we are looking at 116 supersymmetric states in n equals to 4 super Yang-Mills theory. These are labeled by five charges. Two charges JL and JR are the angular momenta in the bulk ADS, which is dual to n equals to 4 super Young, and three charges Q1, Q2, Q3, the R charges, uh, they correspond to the rotations in the internal space S5 of ADS 5 times S5. Now we can use the ADS safety correspondence to find the number of supersymmetric states with some given value of charges. Now suppose these charges are of order n square. What we can do is we can find supersymmetric black holes in the dual ADS 5 times S5 with the same charges and use the famous Bekenstein-Hawking entropy formula to find the entropy of these states by just computing the area of horizon of this bulk solution. However, there is a question. The supersymmetric black holes which are known only lie on a four-dimensional subspace of this full five-dimensional chart. So the question is, are there e to the n square states away from this four-dimensional subspace or not? And in this work, we argue that the answer to this question is yes. Now, what we do is we use the supersymmetric generalizations of gray galaxies and dual dressed black holes. These are the solutions that we propose that we the solutions that we proposed as endpoints of superradiant instabilities in these two papers. Very basically, gray galaxies are black holes which are dressed by gravitons with very large angular momentum, and dual dressed black holes are black holes which are dressed by deep sea brains which carry very large angular momentum on S. Okay, and the simple idea is explained in this special case where three of the charges Q1, Q2, Q3 are equal and they are labeled by capital Q, and JR is put to 0. In this case, it's a two-dimensional possible supersymmetric space. However, the black holes only lie on this one-dimensional black line. So now what we can do is suppose we want to find the entropy of supersymmetric solutions at point A. We go vertically down and we end up on a supersymmetric black hole, and we dress this black hole with angular momentum which is carried in this vertical line in the graviton gas which makes this gray galaxy. Okay, so we know the entropy of solutions everywhere above the black line by forming gray galaxy. Similarly, on the right hand side, what we can do is we can dress a black hole with a dual giant graviton which carries very large angular momentum along S5. So we have supersymmetric versions of dual dressed black holes below the black. And therefore, we see that using these two solutions, we have covered the full two-dimensional space. Now, there is a quantity called superconformal index in n equals to 4 superangles, which is protected against coupling. And therefore, we can do calculations on the field theory side at weak coupling, and they are supposed to be true even at strong coupling where gravity is classical. So on the right hand side, uh, I have the prediction of the superconformal index from the bulk. So this blue solid curve and blue dotted curve is the prediction of the superconformal index if the supersymmetric states were only on the black hole manifold. However, this black curve which deviates from the blue dotted curve is a signal that the gray galaxies exist. So these solid curves are what we predict from these bulk solutions, and we numerically computed the superconformal index in the field theory, and we got and the numerical prediction is this red dotted curve, and we see that there is some prediction that the these new solutions exist from this numerical calculation. And thank you, and I welcome to come to my poster and have some very interesting insights.